We've reached some velocity here with a story that we've been trying to build with our partners here for a while. But one of the ways in which this will be more public is HPC Wire is here, the guy with the camera and an audio plug-in in the back. So in 4 or 5 days, we'll be able to put panels on HPC Wire and be able to share some of the story. This stuff is just not repeatable other places because we can't capture it. We've got all the smart people in the room here, and we've just not done a very good job of that. So that's just one thing to keep in mind. Keep looking at HPC Wire. Secondly, I won't call this a shameless plug, but let me just call it a plug. This is written by and for you guys. So I was rather coerced into getting involved with this a couple of years ago. This has been 2 years in the making, trying to tell a story about the industrial use of HPC. Cynthia and I have been working on this for a while. We've had I think it was snowy days in Washington when we were running around place to place with the 4 companies. These stories are not easier. Because these guys don't typically tell those stories, okay? Now, a couple times we have. So, we've got in here, good story from Rolls-Royce. We've got a use case in here from BP. Got a use case in here from GE. The water freezing molecule issue is in here. We've got an endemic chapter. Cynthia's helped put this together for that. We have stories that have come from you to make this happen. There is no such other place where we've been able to put together those kinds of stories. This is written so my wife can read it. Yet still not embarrass ourselves in front of you most technical folks in the room. So if that helps, I'll tell you instructions on how you can get those here yet today, but it really, the demand is out there. Cynthia and I have talked about this quite some time. The demand to tell a story in Washington, the demand to understand how HPC needs to be done a little differently than what we have done so far is a story that needs to be told. So that said, we want to get into this relevant scale. We have no slides. Really do want it, but I found and learned something in this conversation that I think is, in addition to relevant scale in computing, it's relevant time. I'm hearing that repeated again as well. So let's just sort of throw that on the table. I heard that several times today. If it's not done in the relevant time, we can't even start. Now, so the story we sort of had yesterday is if we can't do the relevant scale to meet the science demand, why start? But I'm also hearing a little bit about that relevant time. So how do we, now we've had these conversations and sort of teed it up, how do we as a community in HPC and data rally to be able to change this behavior from mostly R&D really to production and take advantage of today's resources, take advantage of what Bill Kramer said is coming down the pike, the astounding increases in capability that are coming here. So the relevant scale notion was originally something north of cloud and south of exascale. So Mark Seeger even said it pretty well here a bit ago as well. As you know, this isn't exascale that we need to get to necessarily, but somewhere south of that. Interestingly, Chris Mustaine, the council data, you've got folks, survey data, says we want 10x, we also want 100x, and we also want 1,000x better than where we are today. Wow, now that's pretty impressive. So there is demand out there, but Lynn, what are the cultural barriers? You know, what are the behavioral issues to do all this? It's not all just technical. So let's begin with, can this be done with industry? What are those issues? We've been talking about it here for quite some time. Introduce yourself, where you're from, but Jim, I'd like to start with you. You said something in our conference call last week that really struck home, and if you can share that a little bit, I think that might be helpful. This code development that was going to take maybe several 100,000 cores of work to get to be able to run then at some relevant scale that was not several 100,000 cores. That whole process, that demand, what does it do for you? If you can share any of that, that'd even be helpful too. But why don't you start with sharing a little bit about what this relevant scale really means in your kind of business. Then share with this crowd what your business is.
Okay, so my name is Jim Mellon. I'm the Global Head of Research Informatics for Syngenta Crop Protection. We talk a lot in this community about our biotech. We're actually the world's largest maker of agriculture chemicals. So we have a chemistry business and we have a seed biotech business as well. So we have a big push and a big strategy towards computational science, and that is replacing the traditional wet sciences, the traditional field trials, where we are really trying to do some predictive science, computational science, to get better products and get them to market much faster. We talk a lot about the biology side, the genetic side, because it's so immature. Chemistry side, chemistry's been around for hundreds of years. Biotech is relatively new. So we do a lot of our own algorithm development. We use a lot of open source. There's not so much commercial code. There's some in that space. There's more in the chemistry space. So we have a lot of scientists who do their own, and this is, I think, common in our sector in the genetics, is we have a lot of grad students developing codes. We have scientists who only develop because they had to learn how to do it themselves to get by. And they kind of hang around in that prototyping space. And when they get a prototype, yeah, it works. Okay, give me 50 user accounts and let's turn this production. Let's start cranking it. I said, well, wait a minute. You know, it's not at the scale that we could run multiple times with lots of users. So we've got to get the behavior and the capability to start developing for high performance compute at the beginning, because you can't bolt it on later on. So it's a lot of you know, that education, how we get the right talent and things like that to start thinking along that lines. Another issue we have is, and I'm going to talk about a different kind of scale rather than just cores and things like that, but it's the relative scale of science. So we have, and this is the behavior of a lot of the people doing the modeling and the simulation, is they want to build the super model that's going to, so we've got sensors in fields, we've got drones flying over fields, we've got sequence data, all this kind of stuff. We will make the perfect model. Let's fund something that in 5 years we can plant rice in the Sahara Desert. You know, it's not probably going to happen. And if you go to senior management for that kind of funding, they're going to say, I just don't believe your basis for that return on investment. So now it's really coming back to heuristics. What's relevant today? What's relevant in the next year? So if I can show what if I can increase yield in North Dakota in corn in 2 years by 5%, all of a sudden the corn business says, wow, if you can do that, then you've got us backing you. What if we can reduce the effort in a field collecting data, because we can fly a drone over, we can reduce it by 30%. Now you got your operations people saying, yeah, we're behind it because we're saving money. So it's these small things, improving things out, these proof of concepts that's going to get the funding for the big things down the road. And the big things will come, but you've got to start with what's relevant for tomorrow in our space with our company. And it's that whole funding basis and how you get, you know, you're competing with sales, the commercial space, you're competing in R&D with, I need a new combine just to harvest my field. So, you know, making the business case isn't always easy. And it's you can't separate the IT from the science anymore. So I'll kind of leave it at that as a start. Is that all right?
All right. Srinivas, we'll just go in order here.
Sure. My name is Srinivas Tamarakota. I have a responsibility for simulation software development, process automation, and HPC applications. So at Caterpillar, HPC is also very foundational in order to achieve our product development, quality, velocity, and innovation goals. By having access to relevant scale computing, our engineers will be able to do a lot more simulations early in the concept phase and explore a lot of design alternatives, do trade-off analysis, do DOEs, Monte Carlo simulations, understand the effects of variations because our equipment operates in many operating conditions. We have different types of equipment. We'll be able to understand the effects of all those variations on our performance, durability, and things like that. It allows our engineers to do all of those way early and make better design decisions early in the product development cycle. And we also have simulations that run like weeks and to some extent maybe even months, depending on the type of simulation we are performing. And some of these are also like scaled models. These are not even full system models. So you can imagine when we start using full system models, how long they will run. So we definitely need to have access to as much compute capacity as we can get in order to get these results faster, because speed is very important in our case to make design decisions faster. And related to behavior, definitely having access to adequate compute resources will change the user behavior because they'll be able to model more complex systems and get better insight and not have to make a lot of assumptions and things like that, because they can model the system in great detail with adequate complexity to improve confidence in their predictions. Okay, so that also leads to a little bit of better success stories to get the ROI, to get the investment going, and also it helps in democratizing simulation across the enterprise as well, because there is more trust that is built in using success stories, using confidence. We'll be able to deploy these processes to many groups within the company and ultimately lead to culture change. Now, we also use combination of in-house and commercial tools, so therefore having access to compute resources is great, but we also need to have affordable licensing models. So when we have both put together, I think we'll be able to really change the culture.
There's that culture word again. Thank you.
Well, I'm going to build on culture.
All right.
And behavior. So Don Brettel, P&G. I'm the Associate Director for Modeling and Simulation in Corporate R&D at P&G. So what we're trying, my group's main mission is building new capability for the business, be able to model things we haven't been able to model, enable modeling, get access to high-performance computing, make sure we have adequate resources for doing that job. But so I'll, like I said, I'll pick up right from where you left off on the cultural change. We're been on a journey for probably 2 decades, trying to explain this better to especially to our management. One of the things we've run into is at our highest level, our company is understanding. We've shown enough benefit. At the lowest level, we've got a lot of people wanting to do this, and we've run into some misunderstanding in the middle, I would say. So what we're starting to do is actually run a modeling college. We call it Modeling College Leadership Workshop, and it's basically taking our middle upper managers by the hand and carving out a half a day and teaching them. Actually, first thing we do is we tell everybody in the room that modeling's your job, which freaks some of them out, right? It's everybody's job to do modeling, right? So that's a real paradigm shift. It's not the modeler's job to do the modeling all the time. It's your job to demand it, to ask for it, to ask for learning plans that learn primarily through model, right? So that's been a fairly new shift, I would say, in the last couple of years that we're starting to change that conversation quite a bit. about whose job it is. So part of what we have to do then is provide the tools. So I agree with what you guys said before me. We're doing all those things, but then, all right, you're telling us, but can you model this physics? Can you model that physics? So then we start to have a useful dialogue about, because they're now going to be demanding their organizations do modeling work. So, democratization, we've been on that journey for about a decade now, creating automated workflows. That's spiking our HPC usage tremendously. Not at extreme scales yet, but as far as the amount of jobs that roll through our HPC is going up dramatically, because those jobs can be requested by any average engineer. Doesn't have to know anything about simulation, just needs to know that they need certain simulations run, just like they would run a battery of physical tests. Just get that same battery of virtual tests done first before you ever build the first whatever you're building. So we're on a march to do more and more of that automation, to reuse a lot more of our models. Most of our models today still sit on somebody's hard drive, not searchable. So we're investing in SPDM, be able to automate that work every expert's workflow, and be able to reuse and find that work. I'll just say the last thing on the very, very large scale work. What's relevant scale and why do we need it? One of the things, the way we use those kind of simulations is to have what I would call early in a design stage what we think is as close as we can get to the truth, right? A realistic simulation with all the right physics in it. With the capabilities we have today, we still have to make the shortcuts. We still have to change how we do our simulation in order to get a pretty close. So the more we can feel like we have the right answer early on, we can then build reduced orders. We can take some of the shortcuts, and we at least know at that point what those shortcuts are costing us in getting the right answer. And in many cases, we take that simulation and we reduce it all the way down to differential equations that approximate, because we may be running an optimization simulation of a very complex production system, and we just need it about right? So we can take that very complex simulation, reduce it down to if we're trying to reduce energy, right? The things that make sure we have the energy usage of that process right, and then use that, because that's then at a good enough scale. But we have some confidence that we were simulating, we had the best simulation possible from the beginning. So that's actually what that LS Dyna run was at 15,000 core, right? That was expanding what was really a very small segment, expanding out, making sure that our boundary conditions were actually correct.
Don, you just said something that struck a chord with me. You talked about the modeling. Rick Arthur had just said a couple of weeks ago that maybe the mantra for kids should not be, you all ought to be coding, you ought to be modelers. Do you agree with that?
So I have a son going into college. I'm telling him that.
Good.
So
okay.
Yeah, I would definitely agree. I mean, coding is a means to an end to do something, right? So you're using coding for to what end? And so what I think is exciting to students is and we have, for those that don't know, we have a simulation center at the University of Cincinnati. We have 50 postdocs, graduate students, undergrads doing modeling simulation day in, day out for us, being mentored by professionals in the modeling area. But the coding is to an end. Is it to make a fraction of a cent on a trade? Is that what you want to do, or do you want to solve relevant, solve physics problems? What do you want to go do with this great power and computers that are out there? And I think when you talk about it in those terms, it does get exciting actually to students. I mean, I see it every day at our simulation center. They're excited about these challenges, and they can't believe the kind of physics, chemistry we're trying to solve with computers.
Todd, you have no such challenges, do you?
So I'm Todd Simons. I take the lead for high performance computing at Rolls-Royce. I'm in the design systems engineering group, and I'm embedded still with the group that's developing software for modeling and simulation. So It might be worth mentioning Rolls-Royce doesn't make cars anymore. That was spun off in '71. We make gas turbine engines, so it's a high-tech product. It's a very competitive marketplace. We rely heavily on modeling and simulation, mostly computational fluid dynamics and finite element methods to make competitive products. And we're constantly pushing on all of the parameters that make a product competitive, so reducing weight, increasing performance. And so I think the relevant scales, some of the scales that I end up thinking about are the time scales, and what sometimes dominates is the design cycle. So in terms of the design cycle, and there are a couple of different scales to talk about. So we use both internally developed software. We rely on a lot of internal software. We also use commercial software. So in our software suite, we really use a wide variety of high fidelity and low fidelity tools. So early in a design cycle, we end up using tools that are older. They run very quickly. They're lower fidelity, but they help search out the design space. As we get into detailed design, we end up using higher fidelity, more computationally intensive simulations. And then there's some of the really big simulations are pre-test and post-test validation to make sure that our modeling techniques are capturing the physics that we need to capture. So one of the cycles is the engine program cycles. So a lot of the thinking about technology and developing new capabilities in the modeling and simulation software that we develop tie directly to engine programs that are about to kick off or on the horizon. There's a roadmap of what we need to have ready when. And the same is true for having the capacity for running these simulations, the high-performance computing resources. So all of those investments tie back to the return on investment. It's nice to hear a lot of discussion about the business case, because that really is critical in terms of making investments. The company is very focused on what we need to deliver in terms of engine programs and the cost associated with that. So there's got to be both for developing software and buying computing resources, they have to tie back to engine programs that need them. So you've got to have a demonstrated need and chief design engineers that will sign off that this is a requirement. And then I think, just the larger, not just engine cycles, but the larger business cycles really affect everybody in our industry. And case in point is there's no one here from the oil and gas industry. So aerospace goes through the same cyclical business cycles with boom and bust. So that's something you need to be cognizant of, trying to invest in capital-intensive resources. So I think the other relevant scale is that might be worth mentioning is in terms. So from the engineering groups, there's really people really want two different things. And on the one hand, we'd like our simulations, the ones that take a long time to run, we'd like those to be 10 times faster. And for medium-sized jobs, we'd like to run 10 times more than we're able to run now. So those are some of the pulls.
I'm just going to ask one question of you, and then we'll open it up to the audience. So there's another relevancy in here that we've heard a little bit yesterday and some today, is what's the relevant level in the company for the champion? And who is that audience that you have to sell? Is it the boardroom? Is it the CTO? Can this be sold at the director level? You just talked about chief engineers. What's that relevant level where those choices get made to invest and where you have to work through is it a zero-sum game and I have to arm wrestle with somebody else, or can we expand the pie with modeling and simulation and do things we've never done before? What does that look like culturally inside your companies? Todd, since you were on a roll.
I spent some time doing that. So it depends whether it's an operational cost or a capital cost.
Okay.
The approval process is different. The bigger the amount of money, the higher up the organizational chart you have to go. So I think, if we're, but the truth is, computing is getting expensive. So it would probably go up pretty high when we're talking about expanding capability and growing for future, the grand challenge problems that each of us have in our organization. The ones that are, even just 5 years out, that requires a considerable investment, so.
Got one thing for your answer, which was perfect. It depends on whether it's CapEx or OpEx, and that's a helpful understanding. Don?
I disagree.
All right.
Computing's not expensive. Experimentation is expensive. Absolutely. That's what's expensive. We are going through a process right now with finance as our best friend right now, because we are asking them to go through the R&D budget and tell us at a corporate level across the globe, what are we spending in every area, right? We know about what people cost. It's frightening, shocking, silly, all these things, what we're learning from that process when you compare what we spend in certain areas of experimentation compared to when you count all in, everybody doing simulation, all the software, and all the computing. It's almost not on the radar screen, at least at Procter & Gamble. And we think we're actually doing okay relative to a lot of people. So that's our latest tact, I would say, is like we can't afford not to do this. We can't afford to keep doing what we're doing already experimentally. It's too expensive. We already know that. So what we're finding is we have some courageous leaders that will say, you know what, you're right, that are leading major areas of businesses, vice president level, and says, you're right, we are spending way too much money on experimentation. I'm going to cut that budget in half. And we might, if we have a good modeling proposal, we might give you some of that back.
Whoa.
That changes behavior very, very quickly.
Did you mean physical experiments?
Physical experiments. Yeah, no, not. We don't talk about our virtual experiments very, very often. We talk about it as modeling. So it's very difficult when we talk at we need more investment generally in computers and software licenses. We get a lot of, we've been managing that at a flat level. It has to come from somewhere else. You're trading off something, and for us, we have our gun sights on experimentation. Doing less experiments is how you pay for this. Full stop.
Powerful.
Check when you said that. So that money got transferred to your budget? No.
Well,
Or is
not,
it gone?
Not yet. So part of it's savings. We only ask for a small fraction of that savings as all we need to invest because we spend so much in the experimentation area. We don't need all that money. So that's a conversation we're having right now, where it's a relatively. It's a concept that was put in place probably, Tom, you lived it 20 years ago. There's been pockets where this has been done successfully, and that drove to very high levels of adoption of modeling and a complete change of the work process. So we have very narrow pockets, experiments we've run through our history in our company where it's been successful. So we're pushing to make that more the norm across our businesses on how we think we pay for it. Because if it's all incremental, if it's somebody's decision, we kind of get into gridlock. We haven't had a lot of success, but we have to show how it's going to pay for itself.
So I agree that experimentation is more expensive. It's just that there's not a National Diaper Safety Administration
That's right.
requiring destructive testing The testing, the testing on gas turbine engines is that's a requirement, and we know we're gonna run some. Okay, there is. All right, that's in your budget too.
How many times can you fail? Right? How many times can you
Right, that's right.
intentionally do it and screw up? Right? That's the trick.
Yeah,
But
that's.
bigger consequences die for the engine, though, isn't it?
That's right.
Diapers would kill more people.
So the testing has to be done. We know we're going to do that. It's
And
where
and
we might
always
be.
run. Yeah, we always run the last. Of course, we run the last test, but hopefully it's one test and it's straight to production.
But you're right. Yeah, it's less expensive than testing.
Caterpillar have it all figured out?
Trying to. So we also do investment proposals. They go pretty high up in the company. And a lot of what we do is collect value story and try to use the value to kind of, make a case that this is a, very good investment, and also, make a case that there is no other way we can do in order to meet our, product development quality, velocity, and innovation goals. So simulation is the way.
Wow, so when you say there's no other way to do it, that's your story, you're sticking to it and it works?
I mean, that's been, we've been hearing from all other companies too, right? So
Yeah.
we have to use simulation in order to achieve our product development goals. So, that coupled with the value it generates is the, story that we've been
Okay.
using.
All right. Jim?
So our approach, so we have our executive sponsorship from the head of R&D and from, it's basically our chief operating officer. You got to convince them, you've got to have some champions on that board, but in reality, the next level down, the head of the business units, the ones that are going to make money, those are ones that you've got to show some value as well with some quick wins. We're also, part of our business case is we can replace, we do 100,000 field trials a year. We can do 20,000 field trials a year because we've got the right models and the right simulations in place. There's a real business value there if you can get them to believe the basis for your return on investment in that case. The other approach that I'm taking, I'm trying very hard to operationalize the cost of the compute power. And we talked about that. Capital, you got to go, certain levels you got to go to the executive committee and things like that. Don't want to have to go there if possible. But we're also trying to leverage savings from a model of traditional third-party utility computing centers, which for R&D work is very expensive because everything is non-standard. So we are trying to keep a piece of that savings by moving to a different model, whether it be cloud or NCSA or things like that. There's a real case for making that move. I'm trying to reinvest that money in technology. So, but yeah, and it's really shown the quick wins is really helpful. As I said yesterday, sometimes we can just show how you make less bad decisions. A few of those, that goes a long way sometimes too.
Less bad. All right. You guys answered those questions so well. I'm going to make the executive decision to move on to the data panel now, so we can. This was wonderful, actually. The really cogent, quick descriptions of the kinds of things that are going on at this rate are wonderful. So, thank you very much.